start off, what is a siphon? A siphon is a device used in engineering that can be utilized to move a liquid from from a higher altitude to a lower altitude through a tube or a pipe. One of the biggest advantages of using a siphon is that they can be used to transfer liquids between two containers when there is some obstacle or barrier in the way that would not allow the liquid to flow through normal means. Minimal external energy is required, as you would only need to push the liquid through the pipe or the tube by first creating some form of vacuum on the lower end. Afterwards, the difference in atmospheric pressure and or the gravity push the liquid through the pipe or tube into the level of both liquid and the containers is the same. So you might be wondering what the applications of a siphon are. There are actually various real-world applications of a siphon that are used in our day-to-day lives. Some of these applications include siphon rain gauges, siphon spillways, used in dams, and the modern toilet. There are also other siphons that are not classified as true siphons. These include siphon coffee makers, inverted siphons, siphon pumps, and venturi siphons. Another way that the siphon can be used is to siphon the liquid from a hard-to-reach container into a more accessible one. For example, you can use the siphon to transfer the gasoline from the full gas container into some form of a fuel can or something, and then use that fuel can to fuel up your vehicle, whatever it may be.
So based on this experiment, here's the equipment what we have. We have paper and pencil to collect data, and as well as 3 cups, 2 siphons, and a box that we made for our height. And here's the extra siphon tube, scissors to cut off the siphon, measuring tape, as well as food coloring, a timer to visually demonstrate a siphon. So the objective of this project is to test how the fluid flows between 2 or more containers at different altitudes using siphon in order to better comprehend the concept. In addition, we changed the temperature of the water to see how to affect the flow rate of the water through the tube, how long it would take to compare to other temperatures. Those objectives, we're going to use the Bernoulli's equation that help calculate the results of what we need to determine for the results.
Pressure and all that.
So we have conducted the results of our experiment from what we got from cup A to cup B. So from pressure 1, we stated that it was atmospheric pressure. To define the pressure 2, for cup B was 101,692.4 PA for P2. Then we defined the pressure for P2 to P3 was 102,084.8 PA for cup C.
And that's the change in pressure from changing the height of different siphons.
Yes.
In a real world application, let's say this was increased by 10 or 100 times the size, you would have the size of this would be 100 times more, the length would be 100 times more for the siphon tubing or with the pipe or whatever. The difference in height would be multiplied as well by 10 or 100 or however much whatever the height difference would be, you would use the Bernoulli's equation to then figure out the pressure in between the containers. If you were to keep the same diameter for all the pipes, well, you wouldn't have to change the velocity. It would be constant, so you would just cancel them out on both sides of the equation. But if you were to change the diameter, you would have to calculate the difference in velocity and such. In this real-world application, the top one would be exposed to atmospheric pressure, while the bottom ones would be more underground, so they wouldn't be exposed to that pressure. So the pressure would change, and we would just use Bernoulli's equation to figure out that pressure. And for the theoretical problem, this one, the theoretical part comes in that you would have to multiply all these numbers by around 10 or 100, depending on how big the containers and the tubing and everything is for like a real world pipeline. You would get all these different numbers, like the different flow rate. You would calculate how long it would take. Well, first you check the volume and find the volume of your container and divide that by the amount of time it takes to fill up that container, and then you would get flow rate. For this one, we did both cold and hot. What we figured out was that for the cold one, there was a faster flow rate compared to the hot one. The hot one filled up in 68.37 seconds, while the cold one filled up in 36.65 seconds, which is half of the hot one, a bit more than half of the hot one. And from there, since we had the velocity and everything calculated, what we wanted to figure out was if the change in how big the change in diameter would affect the pressure and everything. The pressure change, the flow rate, and the velocity and everything. For if this was implemented into like a large-scale project with big containers and bigger pipelines.